Very much, David. Really appreciate the opportunity to chat with alumni from the four corners of the globe. I'm glad that you've given up an hour of your time to come and hear some of the work that we're doing here at the E.A. Milne Center for Astrophysics at the University of Hull. As David was saying, my name is Brad. I'm the director of the center and head of the Department of Physics and Maths here at the University of Hull. This is a topic that is not one that I thought that I would pursue when I started my career in astrophysics. It's something that sort of came about kind of by accident a little bit. I work on things like the origin of the chemical elements and how the chemical elements get spread around the Milky Way galaxy. And the further I worked on this subject, I started to realize that there were applications beyond what I had initially thought, and that includes sort of the building blocks of life, those chemical elemental building blocks that we think are fundamental for the development of life. And I realized that the codes that I was using, the models that I was generating, had this application where I could at least try to address this question of whether we're alone. I'm not going to answer that question definitively. I will hopefully leave you with an unvarnished assessment of some of the challenges that life faces in getting established in the Milky Way galaxy, and why it is such a challenge to answer this question, and why the answer to that question may not be the one that many of us hope it might be. I probably am not going to sway you necessarily one way or the other, but as I say, it will be an unvarnished look at some of the astrophysical challenges that life faces in terms of getting rooted and established and developing into something complex, let's say. And it's a topic that I think everyone, whether it's a scientist, an active research scientist, whether it's kids at school, whether it's the general public, it is something that resonates with all of us, this question about whether there is some sort of extraterrestrial life out there. And you don't have to look any further than even Stephen Hawking, who we normally think of Stephen as an absolutely brilliant mathematician who applied his skills to the early universe and the extreme physics of things like black holes. But in the latter years of his life, he also, kind of like me, became really fascinated with trying to address this question. And I love this quote of his that you see on your screen now, which captures his thoughts that there is no bigger question in science than the search for extraterrestrial life. And I think, as I say, in some sense, in terms of scientific questions, it probably is the number one question that would resonate with almost every person sitting here on planet Earth. Would love to know the answer to that question, and I'm sure almost everyone on planet Earth has a thought on whether we are alone or not. So that's going to be the theme of the evening. Since I am talking to a number of alumni, some of whom may have seen me speak before, most of you probably not, I just want to say just a few words about your former university, and in particular the department that I now head up at Physics and Mathematics, and maybe some of the recent developments that have occurred maybe since you were here. So just a few words about the center in which I work. When I moved here 6 years ago, and I had in my mind to establish a research center that was embedded within the Department of Physics and Mathematics. And so the Milne Center is what came out of those thoughts. For those who don't know, Arthur Milne, the namesake of the center, he was born and raised in Hull, was a contemporary of Einstein. Arthur was a brilliant mathematician in his own right, had his own theories about the early universe and cosmology that didn't always agree with Einstein's picture, but both he and Einstein got along very well, and Einstein had great respect for his mathematical prowess. And when I moved my group here 6 years ago, took the opportunity to establish the center in his name, being a Hull born and bred scientist, and with his daughter Meg, who is down there in the bottom right, and then the extended family of Arthur's, we established the center. And it's grown over the last, actually, I just realized as I looked at the screen, this weekend will be the 6th anniversary of the establishment of the center. I guess that's on Saturday. Over that 6-year period, we have grown from sort of 0 to 30 staff and postgraduate students. In many ways, I like to think that we are the research leaders of the university in terms of the outputs and our international reach in terms of our research. We have benefited immensely, and was certainly one of the reasons that aided my decision to move here. The university invested heavily in high performance computing. We have a absolutely spectacular supercomputer in the building next to us that we have benefited from immensely, and I'll show you an example of that towards the end. It's one of the most powerful facilities owned by a single university within the UK, with the hopes that we're going to triple or quadruple its power over the next year or so, budgets permitting. It's already a spectacular facility that has made some incredible inroads into answering this question. And the research that we do amongst these staff and postgrads spans everything from the smallest scales, the origin of the chemical elements, through to the largest scales, from galaxies to clusters and the universe as a whole. Maybe one of the things that I didn't appreciate when I moved here 6 years ago, and it's maybe just a footnote in some sense, but it's a really interesting footnote, was that the very first moon rocks that were returned by Apollo 11 were actually brought here to the University of Hull back in '69, I guess in 1970, and were analyzed here. We had a wonderful facility, one of the best in the world in terms of slicing and dicing and analyzing things like rocks, and in this case moon rocks and moon dust. It's one of these things that's been lost to the mists of time, that the very first papers that came out describing the moon dust and the moon rock that was brought back was actually done here at the University of Hull, and it was a timely one a couple of years ago with the 50th anniversary of Apollo 11. But it is a point of pride that we've been able to resurrect, having lost it to the mists of time. Something that they're really proud of, that we played a role in that, the analysis of those moon rocks from the very first moon mission. So, what are some recent highlights from the department? Just maybe some of it comes across as bragging, but these are recent developments, and we're all part of that alumni team. So I don't feel bad talking up some of the things that we've done over the last few years, because we're proud of it, and you as alums should also be proud of it as well. We've gone from strength to strength, from sort of being maybe a very strong department, but one that was ranked maybe in the bottom quartile of physics programs within the country when I arrived in 2015. But we've steadily climbed up these annoying league tables that drive us all crazy. We're now, as of the Guardian league table that came out a few weeks ago, up to number 7 out of the 51 physics programs in the country. And again, it may come across as bragging, but it is something that we're incredibly proud of, and you can see where Hull ranks relative to maybe some of the bigger name institutions around the country. So this has been a remarkable outcome, and a testament to, not to me, but to the staff, the students who have allowed us to migrate up from the 30s and the 40s up into the top 10 in the country, and we're really proud of that one. In terms of some of the research developments, I will show you some examples of the work that we're doing in relation to the science talk tonight, but we've also had some really exciting developments over the last year or so in medical physics, biological physics, and environmental physics, thinking about the aspects of employability and the growth areas in the different employment sectors around the country. So we've invested in medical physics and biological physics. We just appointed Dr. Ji Yang, who is one of the world leaders in modeling pandemics and epidemiological modeling, but also does a lot of work in doing modeling related to air pollution, dispersion, cancer cell cycle, biofuel production modeling. So we're establishing a group in that sort of biological environmental science around Dr. Yang. We've also had some great news recently with one of our students, Kiri Newson, who was awarded Jocelyn Bell Burnell Fellowship last year. This was the inaugural award of what is, I guess, the most prestigious fellowship within the physical sciences within the UK. And Kiri has moved from undergraduate here at Hull and just started her PhD working in artificial intelligence, machine learning techniques for the early detection of cancer, working closely with the medical physics group at the NHS Trust down the road here in Hull. So it's a spectacular outcome and really exciting things going on the medical physics side. And David mentioned in his introduction some of the work that we've been doing and trying to improve diversity in physics. And it's not unique to Hull or the UK, but it's endemic throughout a lot of what we call the STEM subjects: science, technology, engineering, and maths. There is a huge gender gap, within physics. Within the UK, typical first-year cohort of physics students would be about 20% women. Doesn't vary dramatically from university to university to university, and again, it's not unique to the UK. And you would see similar issues in terms of gender disparity in a lot of the STEM subjects, from computer science and electrical engineering and a number of other areas. So we have put a huge focus in doing what we can. This is not a simple thing to solve, but we, with the alumni and the marketing team, but primarily with the physics students within the department here, we set up this campaign, The Changing Face of Physics. It was supported by a lot of students. A number of them are there on your screen right now, including Kiri, who I just introduced. All of them are very passionate about trying to widen participation and improve that gender diversity. When I arrived, I can look back statistically, about 10 years ago at Hull, it was between 10 and 15% of the first year cohort were women. 3 years ago, we got up to about 25%. We passed the national average. And this year's cohort is actually, I thought we were going to make 50%. It's 45% women. I don't know the statistics for every university in the Western world, but this might be the highest percentage in terms of women participation in physics. So we're really proud of that. Was named the best practice in the country by the UK's Equality Challenge Unit a couple of years ago. And we have a new generation of undergraduate students who have picked this up to move beyond just gender diversity, because diversity is more than just gender. And we're focusing now on a much broader initiative about breaking down barriers across the LGBTQ community, race, religion, socioeconomic barriers. It's, again, one of the reasons why I moved here was to position myself in a place within the country where I felt I could make a difference and the team around me could make a difference. So this, perhaps more than any of the research that we have done or any of our positions in these league tables, this is the thing that we're probably most proud of. And a lot of what we've been able to do has been actually supported by a lot of generous donations that have come from you and from the broader alumni community from Hull, who've supported a lot of these women and through internships and bursaries, and every little bit that we've actually secured from alumni has had a really tangible impact on not only this program and our recruitment, but on the career trajectories of the students who have benefited from the support from alumni. So I'll take the opportunity to thank all of you collectively for the support that you have provided for this program, this Changing Face of Physics program. So that was just to give you a bit of context as to who we are and some of the recent developments that we've had within the department. What you're here for tonight is to address this question: are we alone? And as I said right at the beginning, I think we all have our own thoughts on it. If we were all sitting in the room together, we could do a quick survey, and I suspect many of you would put your hand up and say, no, we're not alone. There's got to be something out there. And it's fully understandable why people would believe that. I mean, you just look up at a dark site on a dark night, and you may see 5,000 to 6,000 stars. That alone is already sort of an overwhelming number. But then you compare that against the 100 billion stars that exist within the Milky Way, and the numbers, they become just so large so quickly that it's very easy to think it's impossible. It must be impossible that life only was able to take root on one single planet amongst the hundreds of billions of planets that exist around these 100 billion stars within the Milky Way. So that's what the theme of the evening is going to be, is looking at this question. Now, one of the common questions I get when I'm talking with people, whether it's the public, whether it's school kids, whether it's just sitting on a plane and somebody leans over and looks at what's going on my screen, is this belief that, or this thought that is built into a lot of people, that, well, there has to be life out there because, you know, haven't aliens visited us before in some shape, form, or guise? So let's just look at, you know, you could spend an hour talking about evidence, UFOs, and what they all mean. I don't want to spend all that much time on it, but I want to just touch on a couple of the bits of evidence that have been put forward to suggest that aliens have visited us before. It doesn't necessarily mean, you know, the gigantic tentacle waving aliens that you might see in science fiction films, but alien life nevertheless. This is one of the really interesting ones. On the screen there, you can see it's a meteorite. It's called the Allen Hills meteorite. It was about this big, weighed a few kilograms when it was found in the Antarctic about 35 years ago or so. Now, there have been 50,000, 100,000 meteorites that have been, you know, picked up around the world and cataloged. This is kind of a special one compared to all those other 100,000 meteorites that are out there. First, because we know it came from the surface of Mars, and that makes it not unique, but it makes it very, very special amongst all the meteorites that have been found. But it's extra special because it's a really old meteorite. It was one that was formed, you know, that rock was formed on the surface of Mars probably 4 billion years ago, when liquid water likely existed for a brief period of time on Mars. But the rock, we know that it felt the presence of liquid 4 billion years ago. And as we'll come to in a second, we think liquid water is an important component for the development of life. So it's unique already by being from Mars now, and it's unique because it's really, really old, from a time when water was there. It was probably, like I said, formed about 4 billion years ago. It probably got blasted off of the surface of Mars by some large impact event that came in and threw up debris, and some of that debris, including this meteorite, was able to escape the surface of Mars. And that was probably about 15 million years ago or so. And it wandered around the solar system for a while before it landed in the Antarctic, probably about 15,000 years ago or so. And like I said, discovered about 35 years ago. And when it was picked up, brought back to the labs, put it under a microscope, what did they see? Well, they saw the sorts of things that you see on your screen right there. It's a, you know, if I didn't tell you what it was, you would look at it and think, you know, this looks like some little fossilized remain of some worm. Now, this is really, really, really small. We're talking, you know, you could take like a billion of them and line them up, and it would be about a meter or so. These are tiny little things, what we call nanometers. And it does. It looks, to all intents and purposes, like it could be some sort of fossilized remain of something that was life 4 billion years ago on Mars. And it got a lot of attention, not just from newspapers like The Sun, who had, you know, the headline there you can read, "Life from Mars." It was picked up by media all around the world, got an enormous amount of attention. Bill Clinton, the president of the US at the time, had a press conference on the lawn in front of the White House talking about how our place in the universe, our perception of our place in the universe had changed because we had discovered that life did exist on a different planet, not life that we could communicate with, but life nevertheless. Now, there were a handful of hearty geologists who were commenting at the time saying, whoa, calm down just a little bit. There are things here on Earth that look to the eye like it is life, but it has nothing to do with life. You need to be a little bit more careful before you jump to conclusions. And a good way, you know, a good example to show this is to show you this one. Now, when I show this picture in schools, primary schools with kids, you know, they all squirm and go, ooh, yuck, it looks like a big pile of worms. It's not a big pile of worms. It's effectively, if I showed you the rock that it came from, it looks like quartz. It's just a crystalline rock. It's a sodium, calcium, silica crystal. sometimes called vermicular. But when you take this thing that looks like a rock and you zoom in and zoom in with a microscope, it looks like what you see there on the screen. It looks like a writhing pile of worms. It is not. It is just a rock. It has nothing to do with life. It's just an example of the sort of cautionary interpretation that one has to make when you look at something and think that it might be life. One has to eliminate all of the other potential reasons for it. And in this particular case, over the past 35 years, we've now come to realize that those hardy geologists who were telling us to pump the brakes were actually right. It may look like a duck. It's not a duck. It's not life. It is just a rock. But it was a really exciting development 35 years ago. The other one that people bring up quite often is, well, isn't there life on Mars now? And some of this has been fueled by, we have these wonderful Mars rovers wandering the surface of Mars, taking thousands and thousands and thousands of pictures of the landscape. Some of them are spectacular landscape photos. Some of them are zoomed in on individual features that are in front of the rover. And, you know, if you take thousands and thousands and thousands of pictures of rocks, eventually you're going to find rocks that look like something interesting. And you can wander through NASA databases and see some of these pictures. What you see on the screen there are examples of things that, you know, tabloid newspapers pick up every once in a while and put out a headline story about. In this case, you know, there's a woman sitting on the surface of Mars on the ridge of a ravine, resting. There's a zoom in there, resting her arm on her knee, if you like. You know, there's the claim that, you know, there's a frog there down on the bottom left on the surface. Somebody's left a floating spoon, seemingly, on the surface of Mars. It looks like there's an iguana sitting on Mars. Somebody left a bowler hat. There's a rat sitting there. Even, you know, just over the last few months, we've got more pictures coming in that looks like a partially buried skull sitting there on the surface of Mars, and they're all really, really interesting. Now, I didn't show you the scale on most of those. Most of those rocks are very tiny little rocks. They have nothing to do with life, and if you come back and take a picture a month later or a year later, that rock is still sitting there. It's a psychological, you know, phenomenon. We see the same thing here on Earth. You can go into the Sahara Desert, and there's this beautiful rock there. This is much lighter, much larger, many meters in size. It looks, you know, for all intents and purposes, like a hedgehog when you view it from the right angle. It's the same thing as looking up at the sky during the day and just looking at clouds. You know, if you look at enough clouds, you're going to see clouds that look like cats and dogs and trains, or in this case, there's a cloud that looks just like Winnie the Pooh rolling around on its back. It's a psychological effect called pareidolia, that ability to see things like that cloud, and your brain interprets it as Winnie the Pooh, or that rock interprets it as an iguana. So while it does make lurid headline stories on the tabloids, and they are sort of interesting, they are nothing to do with life on Mars. One that is a little bit more interesting and has kind of stood the test of time a little bit. This was also about 45 years ago now. This was one of the early experiments that had been set up to try to eavesdrop, to listen on the cosmos, to see if there were any advanced civilizations out there trying to communicate with us. This was an experiment in the US. This radio telescope scans back and forth across a large chunk of the sky, listening for non-natural radio signals. And 40 odd years ago, astronomers came in the next day. This was before they saved the data onto hard drives. It was rolls and rolls of paper, and drew a circle around this sequence of letters and numbers there and wrote, wow. Now, what that signal is referring to was that particular evening, that night, there was a 2-minute, incredibly strong, intense burst of radio noise looking at one particular patch of the sky. I got a lot of attention because they spent a lot of time trying to figure out whether it was some internal electronic noise that they couldn't figure out. At the time, the best they could do was eliminate all the potential sources of radio interference. And some of the astronomers came to the conclusion that it could not have been generated inside the telescope or inside the electronics of the telescope. It had to be external. And it got a lot of attention. It's called the WOW signal. You can read the Wikipedia page. It goes through the long history of this signal and trying to interpret what it was. Now we've spent the last 40 years scanning the sky. We've never heard this signal again. Odds are it was some sort of unknown internal radio noise, or perhaps even 40 years ago there was lots of satellites flying around. It could be that some signal from the ground bounced off the satellite and came down into the telescope. So you could be picking up, if you like, a reflection of some source here on Earth. Some people suggested it was a comet that was flying by. Who knows? Even the most avid believers in complex, advanced alien life say, look, it's interesting, but until a signal is heard twice or repeats, you just can't believe that it has anything to do with alien life. And that's coming from those who are the strongest believers. It's still really interesting. There's still those who believe it has something to do with aliens. Probably not. But if you wanted to hang your hat on something that might be aliens, this is probably the only thing that's out there right now that we can point to. And again, like I said, you could spend an entire hour talking about this. Everything from the pyramids through to the Nazca lines in Peru, crop circles, which mostly only ever seem to occur in the UK near major roads, which might cause you some suspicions. This fascinating experiment that someone did in their attic with their Mac and generated this UFO movie that got a lot of attention from 15 years ago or so. If you look carefully, all the trees are exactly the same. It's the same tree that was just composited into different parts of the frame. All these things have been put forward as potential evidence for extraterrestrial life in some shape or form. But none of them have stood the test of time. So that's just to set the stage for what we're going to do over the remaining half hour is come back to this question: are we alone, really alone? Ignoring all the sorts of UFO style things that I've just talked about. What is the evidence, and what is the likelihood, and what are some of the challenges that life faces? So, bit of geography first. This is the Milky Way galaxy that we live in. There's about 100 billion stars in the galaxy. This is stepping out and looking down on it from above. If I turned it sideways, it would be very thin. There's about 100 billion stars, and our sun is no more special than any of the others. It sits sort of halfway out in the disk. And like almost all of the stars, of these 100 billion stars, it happily goes around in a nice circle orbit around the center of the galaxy. Whether you're in the outskirts of the disk, they all go around about 500,000 miles per hour. The stars in the inner part of the disk also go around roughly 500,000 miles per hour. The sun's exactly the same, 500,000 miles per hour going around the disk of the galaxy. We sit in a region between two spiral arms that you can see on either side. We're in a very quiet, sedate part of the galaxy where there isn't a whole lot around us. And we'll come back to that point because it probably is one of the important components for life to develop. Now, we are not traveling at exactly the same speed as the spiral arms. And this is going to be a really important point. It means that every 100 million, few hundred million years, we actually catch up to the spiral arm. We go from a region where there's not much around us to where there is a lot of stuff around us. And I'll come back to that one in just a second. So let's just look at this question of life and think of it as this is the only equation that's in the talk. And think of the equation of life is a bit like a recipe, if you like. You need the ingredients, the building blocks of life. You need an oven to cook those ingredients, and you need a sufficient cooking time to actually allow life to develop. And if you just looked at, say, planet Earth as one example, as the only example we know, it took about 1 billion years for the first single cell life to appear. 2 billion years for multicellular life to appear. Only in the last, couple 100 million years do we have mammals. In the last couple 100,000 years do we have Homo sapiens. So life doesn't appear instantly. It took 1 billion years, and there are lots of reasons for that. But one of the main reasons is that planets start to form, but there isn't a single point where you say, okay, the planet is now formed. It takes time. The planets build up and they get pummeled and they slowly accrete things and get bigger and bigger and bigger. It takes a while for an atmosphere to get established. It takes a while to collect water. There's planets do not form immediately. They take time. So it does, it is only one data point, but it probably does take a few 100 million years or a billion years before things calm down, settle down to allow those ingredients to come together in a stable environment and allow them to start forming something more complex. I'm not going to spend a whole lot of time on the cooking time aspect, other than to say life doesn't appear spontaneously. It does take time for it to appear, and that's probably going to be the case wherever you are in the cosmos. But let's look at the ingredients first. So what are the right sort of ingredients? Well, it's probably carbon is probably a fundamentally important ingredient. Now, there's a lot of reasons for that. If you want to think, or you believe or hope that life is common, you want the building blocks to be common as well. There's an enormous literature looking at other types of life forms besides carbon-based life forms. Like everything on Earth is a carbon-based life form. If you follow Star Trek, you might remember one of these episodes where there's dedicated to silicon-based life. Carbon and silicon are both very common chemical elements. Carbon is one of the most common ones. So again, that's a nice thing if you want life to be common out there. Carbon is really, really common. Silicon, a little bit less common, but still pretty common. But carbon and silicon are very different, even though they may look close to each other on the periodic table. Carbon is this really special chemical element. If you want complex life, you need to move beyond just single atoms of carbon and single atoms of silicon or single atoms of oxygen. Complex life means complex molecules. You need to bring these different chemical elements and get them to stick together into unique, beautiful, complex arrangements. Carbon is almost unique amongst all of the chemical elements. It is a very friendly chemical element. Most of the other elements like to stick to carbon: hydrogen and oxygen and nitrogen, phosphorus, sulfur, all the important ingredients for life as we know it, happily will bond onto carbon to make very complex, elegant molecules. Silicon's different. If you stick something onto silicon, like oxygen, what happens? It turns into rock, and you sort of stopped. Other chemical elements are just not as friendly and do not allow you to generate complex molecules the way that carbon does. So even though we are a carbon-based life form, and it might be a bias, there is sort of a logical chemical reason to think why carbon is an important component of life, because of its ability to create very, very complex organic molecules that other chemical elements cannot. And the other ingredient, and I won't say anything more about the mixture of chemical elements right now. The other ingredient we think that is probably important is water. Water, again, we are a water-based life form, so again, you're right to be at least suspicious that this might be a bias in there. But water is kind of a magical medium in some sense for life to develop. That those first single cells as life are just trying to get started, they're kind of like me and you. They need to feed and they need to get rid of waste. And water is great. It's a great medium for bringing in energy and food from the environment into that single cell, and it's the right medium for flushing out waste material as well. So water is great in that sense. It's also magical, and it's one of the few liquids that when you freeze it, it kind of freezes it. The ice that forms is less dense. It means it floats. When you take an ice cube and put it in the water, it doesn't sink. It floats on the top. So if you are a planet if you are life trying to get established on a planet that is going through, the building phases of a planet where you might have wild climatic changes, it might go super cold for a long period of time, and it might start to freeze. It doesn't mean it doesn't sound the death knell for life, because it freezes from the top, but it leaves the liquid water beneath. So again, those cells that are trying to develop, they can survive long periods of deep freeze because it freezes from the top. Other liquids aren't the same. It's also a great solvent. I mean, you need to extract energy from the environment. Well, anything you put into water, it eventually dissolves, whether it's a body or a chunk of iron, it eventually will dissolve. So water is great for grabbing energy from the environment, feeding the cell, and for sweeping out the waste. So again, like I said, you're right to question that there could be a bias in there, and there may be other liquids that might work. But there are some logical reasons why we do think that carbon and water are at least fundamentally important ingredients for the development of complex life. So that's the ingredients. What about the right sort of oven? Well, if you believe that water is, liquid water is an important component, an important ingredient for life, then you need to have the right temperature. If a planet is too hot, then the water boils away. If it's too cold, it will freeze solid. So there is a sweet spot, a habitable zone around every star where the temperature is just right, sometimes called the Goldilocks zone. So in this plot here, where the number 1 is, that yellow circle, that is our sun. And here's our planets. Mercury and Venus, they're too close to the sun, too hot, no liquid water. Mars onwards, outwards, too cold, no liquid water currently. Again, in the distant past, Mars was probably just inside that blue zone. So there was a brief period of time where liquid water might have existed, which was that whole point with the Allen Hills meteorite that we started with. But you've got the Earth that sits right there in that habitable zone. So there's lots of planets out there, but the likelihood of, not every planet is the same, and not every planet can have liquid water, and not every planet is going to have life, just like in our solar system. Maybe it'll be 1 in 10, who knows? These are statistics that we're still gathering right now. Down at the bottom is 0.5. That's a star that is half the size of the sun. It's not as hot, which means the habitable zone is closer because those stars are cooler. So you need to get closer to the sun to have the right temperature for liquid water to exist. Problem with stars like that is once you get down to that sort of level, you're almost butted up against the star itself. You're actually your habitable zone, your Goldilocks zone is so close that you could have liquid water, but you also get pummeled by nasty radiation and cosmic rays. And it would be very difficult for, again, those first proteins and DNA and things coming together to survive the really hostile environment of being butted up right against the stars. Stars that are maybe twice at the top, that's a star that's twice the size of the sun. Those are hotter, so your habitable zone is further away. More importantly, once you get to stars that are 2-3 times heavier than the sun, they don't live very long. They burn all their fuel very quickly and end their lives before the likelihood that life could actually take root. Those, that if you believe that it takes life, 500 million years or 1 billion years to take root, stars heavier than that, they live, they die, they explode, they're gone before life ever gets a chance. So there is probably a sweet spot in there. Again, stars that are 3/4 the size of the sun to 1.5 times the sun. Still lots of them out there, but not every star is the right sort of star to host planets in the habitable zone. So that's one thing to remember. So maybe there may be lots and lots of stars out there, but maybe only 1 in 10 star fits within the right mass range, and maybe only 1 in 10 planets around those stars sit in a region where you might have liquid water to help life develop. The other thing that might be an important part of the oven is a magnetic field. The Earth is just like a giant magnet. It's a bar magnet. There's a North Pole and a South Pole, and it's responsible for the beautiful Aurora Borealis and Aurora Australis. But beyond that, it serves a more important role. It's a shield. It's a magnetic shield that protects us from some of the things I just mentioned, cosmic rays and nasty things that come along with high energy. If we did not have a magnetic field, these high energy particles would hit the molecules of our atmosphere and knock them off. And it may take time, maybe 100 million years or so, but without a magnetic field, we wouldn't have an atmosphere. And so that's why, for example, Mars, which we always think of as the next best in terms of habitability, it doesn't have an atmosphere because it doesn't have a magnetic field. And so it had water right at the very beginning when it first established, and it had a little bit of an atmosphere when it was first established, but its magnetic field died away really quickly. And because of that, the atmosphere got obliterated. And so it's very difficult to envision life developing on Mars now because of the intense radiation and getting blasted by cosmic rays, at least on the surface. So we do think magnetic fields are important. Again, how many planets have magnetic fields? We don't know other than looking at our solar system, but not all of them do. Venus and Mars don't have magnetic fields. So we do think that these play an important role in terms of establishing an atmosphere. Any sort of atmosphere does require a magnetic field to protect you from these cosmic rays that would destroy your atmosphere. What other things? We have life on Earth. We also have a really big moon. It's a crazy big moon compared to the moons, the other couple hundred moons that we know about in our solar system. There are a few bigger moons around Jupiter and Saturn, but Jupiter and Saturn are much, 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 much bigger. So the moon, you could fit, it's about 1/100th the mass of the Earth. It's about 100 moons would weigh about the same as the Earth. Now that may sound like a small number, but it is wildly different from all of the other moons that we know about. All the other moons are inconsequential compared to their planets. Why does that matter? Well, it helps keep our climate stable. Now, when the Earth goes around the sun, it's tilted a little bit and it goes around the sun, but it stays tilted always at the same angle away from the sun. That's what drives the seasons. If we didn't, we've got a gigantic moon that's also going around us every month at the same time as we're going around the sun. That big moon it's a stabilizing influence. It keeps the tilt of the Earth very, very stable. If the moon was further away or much smaller, the Earth would be more like a bowling ball kind of going around the sun, not like a bowling like every year, but what it would mean is that on geological timescales, we would have much more extreme climate variability. And that's not the sort of environment you want for life to develop. You want some stability. Having that moon keeps our climate relatively stable on long timescales. No other planet that we know of thus far has that benefit of having one of these big moons to help stabilize it. You can sort of see where I'm going here. If you want life to be common, what you don't want is to have too many things that make Earth look special. Thus far, everything I've said kind of makes Earth a little bit special compared to the 5,000 or 6,000 other planets that we know about. We haven't found any that are in the habitable zone, really, where liquid water can exist. We haven't found ones that have big stabilizing moons the way that we have. We don't know the statistics of magnetic fields, but they're not common in our solar system. String together a lot of rare things, and you start from a really big number of planets out there, and you can start to see maybe the potential numbers start to shrink a little bit as you string together a lot of these rarities. The other thing about our solar system is kind of weird. Like I said, we know we've got about 1,000 solar systems that we've discovered, 5,000, 6,000, 7,000 planets around amongst those 1,000 solar systems that are out there. What we have learned thus far, and this is still work very much in progress amongst these 5,000, 6,000 planets that we know about, is that those solar systems are all really different than our solar system. Our solar system, we have planets that are very small, like Mercury and Venus, Earth. We've got ones that are really big, like Jupiter and Saturn. When you look at other solar systems, the masses of our planets don't look anything like the masses of planets in other solar systems, where planets tend to pile up as either the mass of Jupiter or about 3 times heavier than the Earth. Our solar system does not look like any of the other 1,000 solar systems that are out there. Again, that we don't know exactly what it means, but that's not exactly what you want if you think that life is common. You don't want your solar system to be special compared to all the other ones. The other thing about these thousands of planets that we know about is almost all of them, the thousands that we know about, are closer to their host planet than Venus is to the sun. Now, again, this could be the techniques that we're using to discover them, preferentially find the big ones. That's probably a big part of it. But at least what we have found thus far is that most planets that are out there are much closer to their host sun than our planets are, which are spread out across a much wider range of distances. So again, amongst those thousands of planets that we've found, there are not many that look particularly great compared to our solar system. Now, that takes you from numbers like 100 billion stars, and you play this game of how often, the right sort of stars and the planets that sit in the right place and which ones might have magnetic fields. It takes you from maybe hundreds of billions of potential planets down to maybe tens of millions of planets. Still a really big number. But we have gone from, a really big number to something that's, a lot smaller. And I mentioned this, the spiral arm. So nasty things do happen. Every 100 million years ago or so, we pass from a region where we sit, where there's not much around us, into a region where there's a lot of stuff, the spiral arms. That's where most of the gas, the stars, the dust, most of the action in the galaxy is inside those spiral arms. And when you go from a region where there's not much around you into a region where there's a lot of stuff, you do get a little shock. A little bit like sticking your hand out of a moving car. You're moving from air to air, but you feel sort of a shock from the wind. Another way to think of it is these aerial swings that, in a nice calm day, they all go around in a nice perfect circle. But if you get a short, sharp gust of wind, then, it breaks the symmetry. And if that gust of wind is, sharp enough, you can actually collide these things together. Now, we don't have a wind as we move around the galaxy, but we do move from a region where there isn't much stuff to a region where there is. So you move from a region where there's not much gravity influencing us to a region where there's a whole lot of stuff, which means you go from a region with not much gravity to a region with a lot of gravity, and you get a shock, but it's called a gravitational shock, and it shakes the entire solar system. Now, up here in the top left, those little circles are the planets of our solar system going around the sun, and that's the solar system we normally think about. But if you zoomed out further, and you zoomed out even further, that solar system that we know and love fits into that little white dot in the top left. Our solar system is surrounded by billions, maybe trillions of comets. It's called the Oort cloud, and they're loosely held on by gravity. And so when we hit a spiral arm, if you like, we get a shock, and it shakes us. It doesn't bother the planets, which only really care about the gravity of the sun, but all of those billions and trillions of comets, they get shaken loose. Some of them go flying away, but some of them come flying down to the inner part of the solar system. We've seen evidence of this around other stars, and every once in a while, one of these big things does impact on us. It's likely something like that is what happened 65 million years ago, took out the dinosaurs and 80% of the life species that existed on Earth at the time. So these sort of mass extinction events happen. They're not all driven by sort of impact events like the one that took out the dinosaurs 65 million years ago, but they do happen. Not just here. It happened 25 years ago on the surface of Jupiter, where comet Shoemaker-Levy broke up and left its debris scattered across the top of the atmosphere there. Probably having Jupiter there actually helps because it's a really big gravitational hoover. So some of the comets that do come into the inner part of the solar system have the ability to get hoovered up by Jupiter before they get down to the inner part of the solar system. So what's coming soon in the near future, relatively near future? In 1 million years, and this is before we ever move into the spiral arms, I mentioned almost all the stars are moving around the galaxy in nice circular orbits, but some of them have been nudged and knocked by something that has moved them from a nice circular orbit. And this is a star in the night sky called Gliese 710. It's about half the mass of the sun. It's a different one. It's not moving in a nice circular orbit. Something has nudged it so that it is coming straight towards us like a barrel of a gun pointed at us. And in 1 million years, which is, obviously a long time, we don't need to lose sleep over it tonight, but it's short in the time scale of life existing. This is actually going to pass through our solar system. It's going to pass right through that cloud of comets. And this is a couple hundred stars, and how close they ever get to planet Earth, either in the past or in the future. The main point is this circle down here. In 1 million years, this star is basically going to go right through our solar system. We'll have 2 suns for a while, and it's going to shake loose a lot of comets. The best guess is it's going to shake loose about 10 million comets that are going to come down into the inner part of the solar system. So if anything astrophysical is going to wipe us out on a relatively short time scale, it's going to be that. Now, hopefully, we'll have the disembodied head of Bruce Willis flying around Armageddon style, who will deflect these comets before they ever hit us, if we have the technology and we haven't wiped ourselves out by then. But that's something to watch for in 1 million years' time if you happen to be around. As you go through the spiral arms, you've got a second effect. Stars, that's where most stars are born, are in spiral arms. And the big stars, they live fast and they die young and they die spectacular. And they generate these supernova remnants. All the colors there are fundamentally important because all the chemical elements that we're made out of, our bodies, the screen, everything around you that you can see with your eyes started off in one of these stars, 10 billion years ago. And like any explosion, if it's far away from you, you don't notice it. If you're very close to it, you do notice it. And there's a lot of work going on as to how close you can be to an exploding star before it evaporates your biosphere. The best guess is 20 light years. So the distance you could travel at the speed of light in 20 years. And that's about the size of this remnant that you can see on the screen right there. I put the Earth up there in the top corner. That's about 100 light years away. So it was only 10 million years ago. This is exactly what happened. A star exploded when we were about 100 light years away from it. Not close enough to evaporate our biosphere. If we'd been, closer to here, we would have all been wiped out. Would have taken away the atmosphere and wiped out everything on Earth. That's how close it was. This happened. We know that it happened, even though we can't see it because it was 10 million years ago. It left a thin layer of a radioactive isotope spread all across planet Earth. We know the half-life of that radioactive isotope, so we know exactly when this explosion happened. So these things do happen. Again, we're here to have this conversation tonight, so not every one of these things wipes you out. But navigating your way over hundreds of millions of years that you need to, develop life, or billions of years to develop life, in some ways it's a bit lucky that we've not been wiped out by a number of these collisions or exploding stars. Other planets closer to the center of the galaxy see this effect way more often. So the inner part of the galaxy is probably bad because there's too many stars exploding all around you all the time. If you go farther out in the galaxy than we are, then there's not much in the way of building blocks. There's not much carbon. There's not much other stuff to build complex life. So we probably are in a sweet spot within the galaxy in terms of safety and in terms of building blocks. And on top of all of this, even if we survive these sorts of things that I just talked about, 500 million years from now, which again is not much longer than mammals have been around on Earth, well, the sun is changing. 500 million years, it will be a little bit brighter than it is right now. 5%, which doesn't sound like very much. And it isn't. 5% isn't very much, but it is enough to drive a moist greenhouse effect on Earth, which means basically you boil off the oceans, and the average temperature on Earth goes from 20 degrees centigrade up to 80 degrees centigrade or so. So 500 million years, again, long, long time from now, but still short on sort of geological time scales. Earth will not be, at least the surface of the Earth will not be habitable. We'll have to have moved on by that point in time. So again, this is just one of these extra astrophysical things that life has to face as it evolves. So take all that together. Where are the best places for life? Well, you need the metals, the building blocks, you need the carbon, you need time, so you need stability for probably a few billion years, and you need to avoid supernova. And this is what we do here at the university with my team. We use supercomputers to find out where are the best places. And as I kind of hinted at, it's kind of the middle of the Milky Way where we are. If you're too close, again, you get blasted with supernova constantly. It's very difficult for life to take root in an environment where you're getting blasted by radiation like that. Too far away, you don't have enough in the way of chemical elemental building blocks. Sitting between the spiral arms for a large part of the time is really good. If we were a bit closer to the center of the galaxy or further away, we would encounter those spiral arms more regularly. We're moving at almost the same speed of the spiral arms. It's a special place called co-rotation. So that means we have billions of years, hundreds of millions and billions of years of stability where we don't get pummeled constantly by comets and things. It still happens every once in a while, but it's far rarer for it to happen where we sit than it would be if we were closer to the center or further away from the center. So again, this is another one of these things that you're stringing together a whole bunch of things that conspire a bunch of rare events that make Earth and our solar system and our position in the galaxy look a little bit special. The tools that we use, this is very quickly in passing, the simulation that I just had running on the screen, which is one of these models of the Milky Way galaxy that we're running here. It uses a technique called SPH, smooth particle hydrodynamics. You don't need to remember the name. It's a clever bit of software to model how fluids and gases move and heat up and cool down. It was invented by astronomers 45 years ago or so, but it's now used in all kinds of different areas of everything from natural disaster simulations to the design of artificial hearts, whether it's erosion studies, avalanche studies, aerospace, automotive engineering, designing wind turbine blades for renewable energy, and structural engineering, all using astrophysical techniques that were invented just to figure out how energy moves inside of stars, but now applied into all these different areas. So when I'm talking with students about employability aspects, these are some of the examples that I draw upon, showing the seamless crosstalk between some of the things we do in astrophysics and all of these different areas of engineering and medical physics that build on using exactly the same tools, obviously applied in a very different way. So here I'm going to wrap it all up. We started off, it's about 100 billion stars, just looking at our own galaxy, 100 billion stars. And so you've got hundreds of billions of potential planets out there. Let's string together what I talked about. Probably about 1 in 10 are the right sort. You don't want them to be too big, so they don't live long enough. You don't want them to be too small, because the planets have to be butted up right against the surface to have any sort of reasonable temperature. So maybe 1 in 10 are the right sort of stars where life could develop. Probably about 1 in 10 are in the right place in the galaxy. They're not too close, so they're getting pummeled by supernova. They're not too far away, so there's not enough building blocks. Best guess from observations is that about half of the stars out there have planets around them. That's just what the observations suggest. Maybe 1 in 10 have a rocky planet in the habitable zone, with the right temperature, that right oven that we were talking about. This gets more speculative. Maybe 1 in 10 have a magnetic field. It may be higher, maybe lower. We don't have a whole lot to go on right now, but let's use that as a jumping off point. And again, maybe 1 in 10 have a stabilizing moon that allow you to have long climate stability. So when you take all of that together, you go from maybe the 100 billion stars with hundreds of billions of planets, and it takes you down to maybe 500,000 potential sites for complex life to develop, if you like. And that's using some fairly reasonable, sometimes maybe optimistic numbers. I mean, so it's a much smaller number. It's still a big number, 500,000, but it's a lot smaller than the 100 billion stars that are out there. But there are some, logical, astrophysical, and geological reasons for these numbers. So if you're an optimist, you got maybe 500,000 potential advanced sites for advanced civilizations. Doesn't mean they're there, but potential. If you're more of a pessimist on some of these numbers, you could get down to 500, which is starting to get worryingly small if you think that life is common out there. But again, some of these numbers have some uncertainties attached to them, and the right answer is probably somewhere between those extreme numbers. Now, the question then is, talking about advanced civilizations, how long do they actually survive for to actually communicate with us, if you like? How long can they last for? If you looked at our civilization as one example, in terms of our ability to communicate in an advanced way, you could take sort of the invention of radio as maybe the point where we become have this ability to communicate. Whether we try or not, some of the radio waves that we emit, they're streaming their way across the cosmos. People 50 light years away from us are getting the faint signals of those first episodes of Star Trek, for example. Whether we've signaled them or not, there is radio leakage from the planet. So in that, you could just look at that 100 years where we've been advanced, and we've had a number of world wars during that period of time. We've got pandemics, we've got cold wars, what we're doing to the environment. There's a lot of things out there in even just that 100-year window that are worrying, let's say. But let's just play the game and say, look, let's say we get past that 100-year window, and each advanced civilization can survive for 20,000 years. How many complex civilizations, communicative civilization, might there be? If they survive 20,000 years, it works out to 1. So that's a little bit depressing, given 100 years we've almost managed to wipe ourselves out on a couple of occasions. And even if it's 20,000 years, these numbers work out to about 1 advanced, quote unquote, advanced civilization in the galaxy at any given time. So it's kind of a sobering conclusion. Despite all of that, I really do want to believe, and I do think that there is life out there. It may not be the advanced communicative things that we see in science fiction films, but I do want to believe. Where are we going to find life outside of planet Earth? Probably in my lifetime, it's not going to be out there in the distant stars. It's probably going to be, if it's there, hopefully it'll be in our solar system, maybe in the subsurface, swamp that is down at the South Pole in Mars, small little lake bog underneath the surface there. It could be the icy moons, Europa and Enceladus around Jupiter and Saturn, which are very big balls of extreme salt water, with a couple 100 miles thick layer of ice on top. Every once in a while, the ice cracks and you get geysers of water shooting up, like you can see here in the top right. And NASA has a plan to go to Europa and scoop up some of that water and analyze it in the hopes of finding, again, not Aquaman or piranhas or anything like that, but otherwise the conditions are not crazy for the development of the very first, microbial single cell sort of life. So the hope is that maybe there'll be something there. And if you paid attention to the media, the detection of phosphine in the atmosphere of Venus got a lot of attention. Probably not anything to do with life. But if we're going to find something in my lifetime, the next 20 years or so, it's probably going to be a lot closer to home than some of the things we've talked about. And I'm going to end on this, the only life that we know that is out there, which is extraterrestrial in the sense that it is not on planet Earth, is possibly on the moon right now. This is an Israeli mission that crash landed a couple of years ago on the moon's surface. Aboard it, they had basically kind of like a DVD with little layers, with what's called amber between the layers. Embedded in that were these things called tardigrades. Tardigrades are water bears. These things are the most, they're like the superheroes of life as we know it. These things are almost impossible to kill in heat or temperature or poison or crushing. These things have the ability to immediately hibernate for decades. You can stick them outside the space station for weeks in intense radiation with no air, bring them back inside, rehydrate them, they come back to life. These things are almost indestructible. Sitting on the surface of the moon where this lander crashed is several thousand of these hibernating tardigrades. Some of them may be alive, maybe they're all perished. But if there is life out there right now, it's hibernating on the moon. Didn't start there on the moon, obviously, it was seeded by us, but there could be some hibernating, sleeping extraterrestrial life out there on the surface of the moon. So that's everything I wanted to cover. I hope you enjoyed the last sort of 45, 50 minutes. It's been great hopefully we can do it again in real life in the future. I thank you very much for taking an hour of your time. And if you have any questions, I'm absolutely happy to take them. And just thank you yet again.
Thank you very much, Brad. That was absolutely fascinating, really interesting talk. If anyone does have any questions for Brad, if you want to just put your hand up, you have the ability to, there's an icon at the top of the screen. You can select your hand if you want to ask a question, or alternatively, if you want to put it in the chat, you can do that if you don't want to speak.
See a few friendly faces in there as well.
We've got a few people there with their hands up. So, Daniel, do you want to go first?
Hi, yeah, can you hear me?
Yes, perfect.
Super. So, and sorry if this is a really basic question, but you mentioned that having magnetic poles is important for sort of protecting the atmosphere. What is it that's required to actually have those magnetic poles in a planet? How do we know if they do, as it were?
It's a great question, and so we benefit on Earth because we have this molten iron core, and it's churning away, and so that iron is very magnetic, and it drives the magnetic field. Now, magnetic fields don't last forever because eventually it will cool down. Now, that's likely what happened with Mars. It probably did have a molten core right at the very beginning, but it cooled down very rapidly and lost its ability to drive a magnetic field any further. So having that churning molten core is important. Now, we've been able to hold on to our molten core longer for a couple of reasons. The bigger planet, we got pummeled a little bit more, so the energy that comes from building it up, from being pummeled, generates heat, which is held in the core. We also have the moon going around us, which is big and heavy, which helps to sort of, just like we see the tides in terms of the impact on the water as it moves along, the tides going out and coming in, but it also, it helps stretch and squish the Earth, which drives, it's a heat source to keep the core molten. And on top of that, we have the right mix of radioactive isotopes that are down in that core. There's weird isotopes of potassium and thorium and some other ones that have long half-lives, which contribute to the heat. But none of these things last forever. So there's a lot of work. This is way outside my area, but geologists working on what is the cooling time for the core. And it's probably, crazy long, like 200 billion years, much longer than the sun will be around. But eventually, these things do cool down. So having a molten core is a molten metallic core like iron is probably important. There are ways you can cheat. Like, I played fast and loose with this. I explained why Mars doesn't have an atmosphere because of its magnetic field, and it lost its magnetic field early and the atmosphere evaporated, and that's great. But you could call me on it and say, okay, well, what about Mars? You said Mars. Sorry. What about Venus? You said Venus doesn't have a magnetic field, but it's got a thick, crazy atmosphere, which is true. So it's kind of countered the entire argument that I just made. Venus is a bit unique. It generates a magnetic field, but it generates it in the atmosphere from the interaction of the sun with the atmosphere of Venus creates a magnetic field. It's not intrinsic to the planet, if you like, but it gets generated by its interaction with the sun. And so that magnetic field that gets created in the atmosphere is sufficient to allow Venus to hold on to its atmosphere. Otherwise, it would have had its atmosphere evaporated. But then on top of that, you've got Mercury. So Mercury has a magnetic field. It's the only other planet that we know of that has a magnetic field. It's so close to the sun, it's probably not enough to protect it or hold on to any sort of atmosphere. But one of the questions, and there's a mission that is the European Space Agency called Bepi-Colombo, which is there right now doing close flybys of Mercury. That's the primary question it's aimed at, is trying to figure out why the heck does Mercury have a magnetic field and Venus and Mars do not, even though we have some ideas as to why Mars might not, but why doesn't Venus? I don't know. We can point to what at least keeps the molten core of the Earth molten, and that's what drives that churning liquid and metal drives the magnetic field. But this is much more the realm of geology, and I've more or less exhausted my Wikipedia level knowledge of geology there.
That was great. Thank you.
Peter, do you want to come in and ask your question now?
Thank you. Good evening. That was very interesting. Thank you very much. I'm not a physicist, let alone an astrophysicist, so I hope you'll excuse my my question. I've read about the Drake equation and your little sort of back of the envelope calculation a few moments ago. Kind of reminded me of that. Yeah. Is that still sort of in the vanguard of thinking as to whether there's someone else out there? Yeah, it's a really good question. I've got one of my lecture courses here at the uni. I do frame it around the Drake equation. It's a useful tool for framing the argument, and you can argue about lots of the individual terms and whether it really captures the essence of what life is. And there's a lot of Drake equation snobs out there who are very much against it, and then there's extended versions and Drake equation Mark II that have got extra terms in them. But so yeah, I suspect a lot of serious scientists don't like it, but I think it's a very useful tool for having the discussion and at least the individual. You can't really argue with the individual terms. There's lots of reasons why the Drake equation takes a lot of things I said really is the Drake equation in some sense what I've been talking about. But the way typically the Drake equation gets used or abused is that you think of each term as independent of all the other terms, and it's not really the case. A lot of these terms are interconnected, and it's not as simple as going like the game that I've just played of going 0.1 times 0.1 times 0.1 times 0.5 times 0.1. They're not independent in some sense. So it's useful for framing the discussion, and in a qualitative sense, it's not really wrong. But in a mathematical sense, it probably is wrong. But it quickly blows up into people arguing about it, and should there be exponents on all this equation? And the equation gets more and more complicated to the point that kind of loses its
simplicity, and it's not as useful, at least for the things that I'm doing anyways. But it's a really good, and there's entire textbooks written about the Drake equation and modified Drake equations and how it should be improved. But I don't get into that level of argument.
Okay, thank you very much.
Brad, we've got a few questions just in the chat. I'll read them out one at a time, and then I think that might be a good time to call it a night, if that's all right. So the first question from Paul. As far as we know, is carbon spread equally around the galaxy?
That is also a really good question, and this is what one of my PhD students is working on. It's almost all of the chemical elements. There is more in the center than there is in the outskirts, and it's something called a metallicity gradient, and it's probably not difficult to picture. I mean, most of the gas, there's more gas in the inner part of the galaxy than the outer part of the galaxy. You could see that in the picture I showed. It's much brighter in the center than in the outskirts, because where you've got lots of gas is where you form, stars form from gas, and so you need the fuel to form the stars. And so the inner part of the galaxy has got more stars. More stars means more explosions, which means more carbon and more iron and more silicon, etc., getting spread around. So there's definitely more chemical elements in the inner part of the galaxy, and the outer part of the galaxy, there isn't as much gas, which means there just isn't as many stars, which means there isn't enough chemical elements being synthesized inside of those stars. And so you get a pretty clear gradient, a trend with much higher carbon abundances, iron abundances, silicon abundances, magnesium abundances in the inner part of the galaxy, and it really drops off quite smoothly and dramatically as you step out. So yeah, you've got better building blocks in the innermost. At the same time, because there's so many stars exploding, creating those chemical elements, it means you're much closer to exploding stars all the time, because the density of stars around you is much higher than in the outskirts. It's not unique to our galaxy. Other galaxies show exactly the same pattern of more chemical elements in the inner part than in the outer part with these gradients.
James asks, is it possible to detect volcanic activity on distant planets, as black smokers are a potential home for early life?
I think, yeah, I mean, there's an entire industry based around trying to identify what are called biosignatures or biomarkers for potential life around in extrasolar planets. A lot of work is being done on, and we've been able to detect, the atmospheres of other stars. It's really difficult, but what you can do is, if you've got a big bright star and a little planet passes in front of it, then some of the light from the background star goes through the atmosphere, which is around that planet. And if you've got the right sort of telescope, you can split that light up and you can measure what the atmosphere of that planet, what it's comprised of. And so we've been able to, measure planets that are incredibly, rich in sodium, which is not a great, building block for life, but, you've got planets which are just basically filled with sodium. I think the next generation of telescopes, over the next 10 years, this is one of the big industries is going to be piecing together what is in the atmosphere of these extrasolar planets. We've been able to characterize the mass, the number of planets, how close some of them are to their host stars. So we've gathered a lot of information, but actually piecing together what the atmosphere is comprised of, people have talked about, we might be able to measure chlorophyll in any atmosphere that has any chlorophyll, is some evidence of plant life. Whether I'm not sure about the black smokers, but this would be I'm sure one of the biosignatures, biomarkers that people probably are thinking about. We have one person here at the university who's working on, here within the Milne Center, David Benoit, who is working on characterizing all of the potential biomarkers, biosignatures. He's thinking more along the lines of some of the things that came up, a few months ago when people were talking about phosphine, and is that really a biomarker or not? Well, it's not a clean biomarker, but there's other chemical, other molecules out there which might be clearer indicators of life. The black smokers, good question. I'm going to have to think about what take a little look outside my comfort zone and see what the signatures might be in the atmosphere that might be detectable by looking at the background light passing through an atmosphere that's rich in that debris, if you like. It's a good one. I like that.
Two questions that sort of relate here. Annabelle asks if there might be life on other planets. So determining if there might be life on other planets is that statistically we don't know if life is common or rare because we only have one example. What are your opinions on that? And a related question from Nick is space infinite? And if so, isn't life out there inevitable?
Well, space isn't infinite, but it's really, really, really big. You know, I mentioned there's 100 billion stars in our Milky Way galaxy. There's at least another 100 billion galaxies out there, maybe even a trillion galaxies. So, even if there was one civilization in each galaxy, that's still, 100 billion, maybe a trillion civilizations that are out there, because I've done the game just for one individual galaxy. But there is a kind of a finite size to it in that sense. It might as well be infinite because the numbers become so crazily big, but it is finite. I think the question related to the statistical significance, it's a single point. This is it's the flaw in all of this, is that we have one data point to go on, and the way I presented it, taking the evidence, there are logical reasons for why, like I said, why we think, even though we are a single point, why at least advanced life probably does need carbon. There isn't another element that is as good at creating complex molecules, and any sort of life that is out there, it's got to be more than just elements. It's got to be molecules of some sort. If you want complexity, you need to somehow take individual elements and make them complex. So whatever shape or form it is, you probably do need carbon at some sense. So, but again, it's not unique. There's a whole field around astrobiology, from looking at what's the next best element. People have said germanium, an element that I don't know much about other than I've heard of it. It's incredibly rare, but it's probably the next friendliest chemical element if you want to build something complex. So there could be some germanium-based life out there, but germanium is millions and millions of times, billions of times less common than carbon. So it's probably not rife with germanium-based life forms out there, because it's just such a rare chemical element. And there's other people say, look, again, there's logical reasons why water might be, liquid water is fundamentally important. But again, you might be able to do this with other liquids. But again, there are some logical reasons why liquid water was thought, is sort of unique amongst the liquids. But people have said, look, maybe on Titan, we don't, in our solar system, you've got a moon of Saturn, which has got these lakes of methane, and maybe you could do this with methane. It's hard to imagine what the life would be like, given methane is liquid at such a crazy low temperature. There's not much energy you can extract from it in the same way that you could with liquid water. You quickly get way outside my area of expertise into that. But it is an utterly valid point, and it's the weakest point in all of this. Is we only have one point. On the other hand, a lot of the things that we talked about in terms of astrophysical things that might come along to challenge that, make it possible that we might be the only ones out there, even though I don't necessarily believe that myself. But so I tried to present at least logical reasons why life might not be really, really common, and throw in a few things that maybe you hadn't thought of before. But that is always going to be the weak point when you've got a single point. But if you always have a single point for the next 100 years, we have this talk in 10,000 years, and there's still a single point, maybe at some point you do start to think maybe life really is that rare.
Stephen suggests that in 500 million years we'll have colonized the habitable galaxy.
I hope so. If we manage to not obliterate ourselves before then, or get blasted with comets in 1 million years when they come raining down on top of us, one would hope that we would have moved beyond our single little biosphere, whether it's the whole galaxy, whether it's a subcomponent of it, who knows. But what we can see right now is that it doesn't appear at first glance that some other civilization 500 million years ago has gone out and populated the entire galaxy, because unless they've gotten really good at hiding their presence, and maybe they have, but we don't see any, radio noise coming from the thousands and thousands and thousands of planetary systems that we've looked at thus far. So maybe in 500 million years we will, but it does beg the question, where are the civilizations from 500 million years ago who should have done exactly the same thing and populated the galaxy? Again, it starts to get into philosophy more than astrophysics at some point when this discussion comes up. They're all the right questions to ask, though.
And just to finish off, Chris is asking, I thought that precession was related to the moon distorting the rotation tilt of the Earth. From your talk, it sounds more like the moon stabilizes the Earth. Yeah. So is it? Stability?
Let's put it this way: there's dominant first order effects, and then there's subtle second order effects. And you're absolutely right, Chris, that that tiny little bit of precession is driven by the moon as well. The gross stability is also driven by the moon. So the moon does keep it more or less anchored at what's called the obliquity at 23 degrees from the ecliptic. So the gross effect is to keep it stable, but it does give you this little teensy little wobble at the same time as keeping it remarkably stable. It does allow a little bit of precession as well. You're absolutely right.
Brad, there's a lot of people commenting just to say thanks very much and how interesting the talk was. I absolutely 100% agree with them. It was fascinating, as it always is when you speak to our alumni. I think we'd be happy to hear you talk for another hour and a half. I think you probably deserve to have the evening to yourself now.
My wife would not be happy if I did that.
So I just want to add to the thanks that are coming through from alumni. My thanks. It's been fascinating. Really love having you on board. A lot of people are asking if there's going to be more. We do have 2 more alumni masterclasses coming up in this series, one on Sherlock Holmes, one on horror movies. And next year we'll be following up with some more masterclasses. There'll be another science one, chemistry based. And of course, actually, it'd be great to hear from you guys if you want to drop us an email and let us know what sort of things you'd like to hear from us going forward. These masterclasses are only possible because academics such as Brad are able to give the time and share their expertise with us. And if there's an appetite for something out there that we can deliver, we'd love to share it with you guys. So thanks to Brad, thanks to everybody who's come along, and hopefully we'll see you all again very soon, maybe next time on campus.
I can add just one thing. I can see Annabelle asked about other talks. If you do, I have a YouTube channel, and under the playlist there's something called My Talks. You'll see a version of this one there already, but there's a number of my other talks that are sort of hidden under there. They're freely available if you're a glutton for punishment and want to read something about how the universe will end, or careers in physics, or there's about 24 other random talks in there. But yeah, just if you can find my YouTube channel and just go under playlist, you'll find them there. Again, if you're a glutton for punishment, great. And if you are in Hull at any point in time, just drop me an email. Happy to show you around the center, chat with some of the other students and staff who are working on some of the things I talked about. More than happy to show you around.
Great. Thank you very much, Brad, and thanks to everybody else as well. And have a good night.